Today I will be explaining solution methods for linear problems. Okay, so one of the method that is widely used for the linear problem is finite Fourier transform method. Finite Fourier transform method. Right, this is also called in short FFT method. FFT method. Right. So as you know that this FFT method is applicable only to linear problems, and that linear problems for which the all boundaries are coordinate surfaces. So the very first condition is all boundaries are coordinate surfaces. Coordinate surfaces. What does it mean? That it means nothing but keeping one coordinate constant by allowing others to vary. One coordinate constant, suppose we have x, y and z coordinate. Keep one coordinate constant and vary other two coordinate. Then whatever we will get will be the coordinate surface. Coordinate surface. Right. Now example, suppose x is equal to 0 we are taking with unrestricted y and z. Y and z. So this is kind of yz plane. YZ plane. Alright. So this is YZ plane. Similarly, next boundary could be XY plane. XY plane, YZ plane, or ZX plane. ZX plane. So either these are XY plane, YZ plane boundaries or ZX plane or parallel to that plane. Because if you take X is equal to A, then the YZ plane would be, this surface would be parallel to the YZ plane at a distance X from the origin. So this is parallel to YZ plane. And in 2D, if you go 2D, then suppose this is x axis and this is y axis. So this coordinate plane, coordinate surfaces. So this would be, suppose this is the boundary, right? So parallel to either y axis or parallel to either x axis, right? Or x-axis, y-axis itself in case of semi-infinite kind of thing, boundaries, right? So this is 2D example. In 3D example, you can say the boundaries like, this could be a cube whose surfaces are parallel to xy plane, yz plane and zx plane in 3D geometry. Alright, so this is suppose x, this is y and this is z. This we are taking anti-clockwise direction. Alright, so the boundaries, the very first condition is all boundaries are coordinate surfaces. So FFT method is applicable only to linear problems in which all boundaries are coordinate surfaces. Alright, now once all boundaries are coordinate surfaces, so this will further limit eigenfunction expansion method to domains that have certain regular shape. Okay, so this restriction is not as severe as it first seems, because orthogonal curvilinear coordinate system have been deployed for numerous geometries, right? So the problem that we will be discussing here, orthogonal coordinate system we will take here, just like here taken Cartesian coordinate system. So we have three coordinate system all problems that we'll be discussing will have three types of geometries, three types of coordinate system, right? Cartesian, and next is cylindrical, and next is um, spherical. Now, just like I told you that this is kind of, suppose we are taking a heat transfer problem where the volumetric heat source with a dimensionless value of h. So your equation would be del square theta plus h, that's the volumetric heat source with a dimensionless value of h, is equal to 0. This equation you have to solve. Suppose this is theta is equal to 0, this is theta is equal to 0. So this is maintained at ambient temperature, maintained at ambient temperature, and let's say there are insulation on this side and on this side. So insulation on this side, let me take it with another pen. So insulation on this side and this side means the gradient del theta over del x will be 0 here, and del theta over del y is equal to 0. Now don't be in surprise when I write x means perpendicular direction, right? Here y means this perpendicular direction, normal to this surface, right? Now you see in this problem, if you will have to solve, then theta would be the function of theta xy, right? You have to solve. So FFT method you can use to get the solution of temperature profile as a function of xy. But here what you see that its boundaries are coordinate surfaces, right? Means either the coordinate axis itself or parallel to that. So you see this line is parallel to x-axis, this line is parallel to y-axis, and other two boundaries are x and y-axis itself. So this all four are coordinate surfaces. Okay, so on the coordinate surfaces what you will get, one variable would be constant, and other would be unrestricted. Just like here, if you go, so here it is x is equal to 0, but y is unrestricted, right? So y can go from here to here. Similarly, here the value of x is again constant, but y is variable, right? Here the value of y is constant and x is varying. So these all are the coordinate surfaces. So problem that we will be discussing later on will include the problem in Cartesian coordinate system either, or cylindrical coordinate system, or spherical coordinate system. Okay. Now, moreover, the second condition, though the first condition would be problem should be linear for FFT to solve. Second condition, it must be bounded by coordinate surfaces. So coordinate surfaces. And the third condition for FFT method requires at least one coordinate. Suppose this theta is function of x, y, z, and time coordinate t. So at least one coordinate out of these must be bounded. So at least one coordinate have a finite range. So at least one coordinate must have finite range, not infinite, finite range. That's why the name is Finite Fourier Transform. Finite Fourier Transform. Alright. So for FFT, the following condition must met to apply the FFT. Problem should be linear, bounded by coordinate surfaces. At least one coordinate must have finite range. Then you can apply the finite Fourier transform to solve the problem. Now let's take one problem and move ahead with that problem. Now consider the heat transfer problem like this. Now, as I told you that this all the problem must be bounded by coordinate surfaces. So this would be like this, right? So coordinate surfaces, this is coordinate surface, this is x-axis, this is y-axis, okay, and this is parallel to y-axis, and this is parallel to x-axis. So let's take here x, y all are dimensionless coordinates, and let's take dimensionless temperature here, that is depicted by theta, and theta is function of x and y. All right, now constant temperature, let us maintain the constant temperature on the top and as well as in the at the bottom surfaces of this solid sheet, okay, that is infinitely long. This is infinitely long, so it will move on ahead and it will go like this, okay, so it will infinitely long, okay, so that's we have taken, okay. All right, so the temperature of the sheet is made non-uniform, okay, this temperature of the sheet maintained non-uniform, made non-uniform by an imposed variation along the boundary at y is equal to 0. So at y is equal to 0, we have imposed a variation, and that's how the sheet is made non-uniform. Now the objective is to assess the spatial change of heat, spatial range of that age effect by evaluating uh, theta is equal to theta xy. So the problem statement, if we write, what it will be, del 2 del square theta is equal to 0, right? No heat generation, nothing is happening, so the simple governing equation would be del square theta is equal to 0. Now del square theta, if you expand in two dimension, then del 2 theta over del x square. Remember, this x is non-dimensionless and theta is also non-dimensionless. All right. So this del 2 theta over del x square plus del 2 theta over del y square is equal to 0. Now this is x in this is x is independent variable, theta is dependent variable, but second order, so you need two boundary condition. So you need two boundary condition to solve this. Now two boundary condition, so theta xy, so theta at 0, x is equal to 0, means at this place, at any y, means at this surface I am talking about. So at this surface, if you will talk about this surface, what is that? Theta x is 0 here and y is any y. So theta 0y is equal to what? Theta 0 at any y. X is equal to 0 and x is equal to 0 right here, and y is equal to, let's change a coordinate bit to understand more clearly. If you can change also the coordinate system, right? So you can take this coordinate system. Now let's say this xy, let us flip that, okay? So this is, let's say, y, where everything is going towards infinity. So let's take that x coordinate for simplicity, that this is bounded. So bounded, we will take the x, and unbounded domain, that will be taking y. Now this so here what would be this? So here x, this is x axis instead of y axis, I have assumed. You can assume anything. So you can take y axis as well. So here this would not be like that, okay? So let me erase this. So this would be like theta, and theta, now here x is varying, right? Here x is varying because this is x axis, and while y is 0. So x is varying and y is 0. So x is varying, x is that, and y is 0. So here what is given? It is given that this is x 1 minus x, non-homogeneous boundary condition, and at this place, if you talk about this surface, okay, this surface, what is there? This surface, the theta. So y is varying because this is y axis. See, this is y axis, so y is varying. And what about x? X is 0. So this theta 0 y is nothing but 0. This is given as 0, right? And here the boundary condition, we will write it. So here the y is varying again and x is at 1. Okay, so this height is 1 because we have non-dimensionalized, so this theta 1 y is equal to again 0. Alright, so this is the thing. So the boundary condition that has come up with, so with respect to x direction, if you take with respect to x direction, so theta 0 y means this is equal to 0 and theta 1 y, that is here, it 0. Now with respect to y also, do you need, because second order you need two boundary condition. Okay, so theta here x0 is equal to x minus 1, theta is equal to theta x0 is equal to x1 minus x. But the other boundary condition would be at infinity in this direction, y direction if you take, so it will go to infinity. So other boundary condition y tending to infinity. I am not going to write, I will not write this right now. Okay, so let's proceed with the problem. So why I am not going to write? Because there is no need to specify the location of distance y boundary or the thermal condition. Okay, because there, okay, so theta must be finite. Whatever theta we will get at infinity, y tending to infinity, it must be finite. Okay, so at y tending to infinity, theta must be finite. That means the flux at y tending to infinity would be 0. D theta over, okay, d theta over dy is equal to 0. So these are the boundary conditions. So two boundary condition here and two boundary condition here we got. Okay, so we can write it this as this boundary condition for where theta is equal to y tending to infinity and y tending to infinity as well as at any x. So we will have this, right? So these are the boundary condition and differential equation. These are the setup. Now solution procedure, let's move by step. So step 1, we have to assume expanded form of theta. Theta will be the function of xy for sure, and I will take the summation of one function would be eigen function, that I will write phi in x for the eigen value problem that we need to find out. Okay, second we will take a constant because this is the eigen function expansion. So the solution, once you get the eigen function, solution would be the expansion of that eigen function in series form. So this phi n, now this is the function of x only, so you remained with function of y, so this constant c must be function of y. Since this is n, so this could also be n. The solution will be of this form. Now you need to find out this phi n x. For time being, I will say it, this is basis function. This is basis function. That we will define later on, but this is the basis function. Okay, so In this case, this basis function, I have taken x direction. Why? Because in the x direction this is bounded. If you see this x direction, this is bounded, while in the y direction this is going to infinity, so this is unbounded. So with respect to x, you will have to write the your basis function, and rest will be the function of other variables. So this is the x direction, x is bounded. So let us say, so this is the basis function phi n. Okay, so function of what? X or y. So finite range of x, so we will immediately write finite x, means this would be the function of x only, right? Rest you need the, since theta xy is the function of y as well, so you need another function, convolution of these two function, means combination of these two function. So this function would be the function of y. Okay, so this seems to be variable separable technique, very similar to variable separable technique, because in FFT method, because variable has been separated, one function is function of y only, other function is function of x only. Now what is that? This is the basis function. Okay, so this function I will find out it later, but I will write it here first, very first, what is the value of. So then I will explain later. Suppose basis function is known to you, and that basis function is root 2 sine n pi x, where n is going from 1 to dot dot dot, right? Suppose let's say here also we take because if you take 0 n is equal to 0, then this would be phi n x would be 0. This will give you trivial solution. So obviously n will start from 1 to 2. Okay, and so this will start from n is equal to 1 to infinity. So this is infinity series solution. Solution would be the form of this. Now if we know only phi n x, later we will discuss how to calculate it, then we are able to write the solution like this. Okay, so this phi n x is the basis function. Okay, so what do you think that main thing what you should note, that this basis function n is equal to 1, if you put root 2 sine pi x, n is equal to 2, then phi 2x is equal to root 2 sine 2 pi x, and similarly 3 pi x sine 3 pi x sine 4 pi x. But these are the means infinite number of basis function you will get. But main thing to note is that each of these basic function vanishes at x is equal to 0 and y is equal to 0, similar to the variable theta. Theta, just like theta boundary condition, for theta boundary condition what, this vanishes at the finite boundaries. You see, theta is equal to 0, theta is equal to 0 on this finite boundary, but this not vanishes along this. Okay, so homogeneous vanishes means 0, equal to 0. So this is a homogeneous boundary condition along the x-axis. So this phi n x would have the values very similar to the theta values at the boundaries. Okay, this is vanishes. Each if you take any value of x at the boundaries along this direction, at the boundaries x is equal to 0, x is equal to 1, you will find that this will vanish. Okay, okay, so that means expansion satisfies the homogeneous boundary function in x. Okay, so this expansion, if you put x is equal to 0, this phi n x is phi n x, phi n 0 is equal to 0. If you take x is equal to 1, then sin n pi is also 0. So this is phi n 1 is equal to 0. That means the basis function vanishes at the boundaries. So the expansion satisfies homogeneous boundary condition in x. Now please note that this root 2 factor, from where this has come. So this root 2 Okay, this normalize actually the basis function in a desirable way. So this is due to normalization of the basis function. This came after normalization of basis function. This came after normalization of basis function. So two important concepts that we have to learn later on: how to get phi n x, one thing, and second thing, how to normalize it. Once we know that these two things, we will be easily write phi n x is equal to some a n, okay, some constant, and some function of x. Okay, so this will be written, but this procedure we need to understand later on. Now so we know this phi n x is root 2 sin n pi x. So if we know only c n x, then we will have the solution, because this is still unknown. This is still unknown. So we have to calculate this unknown function. So what is needed to complete the solution is to determine this coefficient that multiply the basis function, means c n y. Alright, so now in this problem basically we will define, let us define FFT of temperature, FFT of a variable. See, FFT could be of variable dependent, let's say dependent, and FFT could be of dependent variable, or FFT could be of differential equation or partial differential equation, ordinary partial differential equation. Okay, partial differential equation. So we will need to understand the FFT of variable first, that is theta temperature. So this FFT is defined in the following way, right? So the FFT of temperature, let's say temperature is the variable here dependent. So FFT of temperature is defined as FFT of temperature is defined as, suppose we have this theta and we have basis function phi n. So this is called inner product of theta with phi n. So inner product of f and g is defined as, in general, this is integral of some range of integration fg product of this, and let's say the variable is x. So this is the inner product, and sometimes some weighting function is also there. Okay, so this is the FFT. So this FFT of variable is defined as, so let's say here the direction in the x direction we have to integrate first. X direction is finite, you see the domain, x direction is finite. So we have to take the FFT in the x direction. Now x will vary from 0 to 1, okay, 0 to 1, right? Now this, what we have to do, this we have to multiply. So let's write in the proper way. Okay, in this way, let's say we are taking the FFT of variable, that variable is theta, and this is basis function phi n. If you multiply these two, inner product means dot product, just like dot product in the vector. Okay, so this theta and phi n must get multiplied. Alright, now you think of this theta temperature is the function of xy. Alright, this phi n is the basis function, which is the function of only x, right? You are integrating, so this product would be the function of x and y, because xy coming here and x coming here. Now you are integrating with x, so x integrate, and then you will put the values of x there. So 1 0, that will be constant values. So you will finally get the function of y here. So some function of y you will get, okay, some function of y. So what function of, let's say, theta. So theta n y. So let me write it again. So theta phi n is the basis function. So for the FFT you must have already basis function. Then you will take the inner product and you will get the value 0 to 1 theta phi n dx, okay, and this would be nothing but theta n, and it would be function of y, because with respect to x you have integrated and you have put the values of x 1 upper limit and 0 upper limit. So x will be eliminated and you will get the function in the form of variable y. So this would be rather this phi, not phi n, this would be theta n x, theta n y, sorry, theta n y. So this is the FFT of a variable. So this concept you must understand. First FFT of the variable, then we will move ahead to take how to take the FFT of the differential equation. So FFT, so what do you understand right here? This phi and y, let me write it. This phi and y, this phi and y is transform temperature. Theta and y, sorry, this theta and y is transform temperature. Okay, just like you take the Laplace transform of ft, Laplace transform of ft, and you will get the function of fs, right? So transform form of ft, Laplace transform, is fs. Similarly, some Laplace transform of function theta, theta is also function of x and y. This is dependent variable, just like ft is dependent variable. So this is, and ft is what, solution also of the differential equation. Here theta is temperature that we are intended to find out, it will be the function of xy. So this is the solution. The solution you are multiplying it with solution variable, means dependent variable. If you take the inner product with the eigenfunction, you will get eigenfunction or basis function. So this is also called eigenfunction or basis function. You will get this theta n y. Means what you see here, that on this side the theta is the function of x and y, and it has been transformed to theta n function of y. Means one variable, once you have taken the FFT, one spatial variable has been reduced. One spatial variable has been reduced when you have taken the FFT one time. What does it mean? That if here you are getting the partial differential equation in theta, you will be getting here ordinary differential equation, right? Similarly, if you have x, y, z, alright, and suppose you have taken first FFT with respect to x, then you have to eliminate it FFT, then you have to eliminate it x, and you will get the value of y and z, and then again take the FFT. Let's say this time you have taken with respect to y, then you will be getting theta n, the variable of z. So you will get from this partial differential equation, you have converted this into ordinary differential equation. The whole purpose of this taking FFT you can understand in this way, right? So let us proceed further to understand. So this is called transformed temperature. So theta you have transformed, theta xy you have transformed to theta n y, theta n y, through finite Fourier transform. So this is the thing that you must understand, okay? So what is that? So transform temperature. So the FFT is what you are taking integral, and from in the bounded, with respect to bounded variable, here it is x. So this is integral you are taking. So this FFT is what type of transform? Integral transform. This FFT is type of, which type of transform? Integral transform. So this FFT is integral transform, that will transform the temperature from two variable to one variable. So that must be understood at this point of time. Okay, so what you see here, this theta you have multiplied by phi n. That means the original function theta is multiplied by the basis function, and whatever result has come, that must be integrated from 0 to 1, that is the finite interval, and the limit of integration corresponds to range of x in the boundary value problem 0 to 1. Okay, in other problems the interval may differ, and the integrand in the FFT generally includes a Bayes function. Okay, so this Bayes function here is this integral transform that we have taken here. It will includes in other problem Bayes function as well. So W here is 1. The Bayes function is 1 here. Okay, so now what is crucial to see right here is that this theta and y that we are getting, this is a function of y only. So this theta and y is, you will see when we have taken the, you will see very soon that this theta and y is c and y almost, means function of y. Okay, so this function of y, you will see, this is crucial, a point I am going to write. What is crucial? That this theta and y is function of y. So this summing, on the summation you will be getting this c and y. Okay, as will be as I go along, I will tell you how. So this, theta, now if we determine this theta and y for all value of n, then this would be the solution. This would lead to solution because we are able to get this c and y. Okay, so now what was the so first we have to take the FFT of the variable we have learned. Now we have to learn the FFT of partial differential equation. How to take the FFT of, next step is how to take the FFT of partial differential equation. So next topic is FFT of PDE. FFT of partial differential equation. So this FFT of partial differential equation, what was the partial differential equation we have to solve here? That is del square theta is equal to 0 in dimensionless form. So we have to solve that del square theta is equal to 0, and that will yield to del square theta in 2 dimension del x square plus del square theta del y square is equal to 0. Now this is the partial differential equation. Now this partial differential equation could be converted into, because you have just seen this theta could be converted into function of only single variable. So this differential equation can also be converted with respect to single independent variable, and means we can convert it into ODE, ordinary differential equation, and using the tool of FFT. So see, if we are taking the FFT of function theta xy, then it will reduce the one dimension and we are getting theta and y, right? And here one independent variable will reduce, so PDE will be converted into ODE by taking FFT. Alright, so you will be getting ordinary differential equation governing this. Here you got this theta and y, and now you need to write this differential equation in terms of this theta and y. So you will be getting theta, ordinary differential equation in terms of the dependent variable theta and y itself. Okay, So an ordinary differential equation governing this theta and y is obtained by transforming each term of the partial differential equation, okay, each term of the partial differential equation by taking FFT. So we will use, now we will take the FFT of this whole partial differential equation. Now how we have take the FFT? We have to multiply the each term with, so we have to multiply, suppose FFT of left hand side of this differential equation. So what we have done here? So when we have taken the FFT of theta, so this is, I will write, this is PDE. So we are going to take what? PDE. FFT means phi n. This is the process. So what we will be writing? PDE. We are multiplying PDE by phi n and with respect to variable x. Got it? So this is right, and we have to integrate it 0 to 1. That's what we are going to do. So this is the FFT. This is the inner product of PDE, partial differential equation, with phi n. So let's do that. Okay. So integral of this del 2 t theta over del x square plus del 2 t theta over del y square, and phi n x is the basis function. So how this is important, see, because it is converting the whole thing into ordinary differential equation. The basis function you must need to find out. Okay, so this phi n x and dx. Now of course if you will multiply phi n x by 0, you will get the 0 itself on the right hand side, whatever be the value of integral. Limit of integration would be 0 to 1, because this is with respect to x bounded domain. Okay, so all right, this is the FFT of this partial differential equation. Now I told you two things: FFT of the variable, dependent variable, and then we need to then once take, then this dependent variable theta of xy will be translated into theta n y variable in single variable. Now we need to find out the differential equation in this theta n y, and then that differential equation will result into will give differential, regarding differential equation you will get by taking the integral transform, that is Fourier transform, finite Fourier transform of PDE itself. Okay, so this inner product and integral transform both are same. Good. So here the weighting function, weighing function is also here, the weighing function is also 1 that we have taken. Okay, now now since the basis function, phi n x and integration do not involve y, only involve x. So the y derivative that you see right here, derivative with respect to y, can be brought outside the integral. Okay, so this second term could be written as, so second term you can write by bringing this outside the integral, because we are taking the integration with respect to x, so this will be out. So let's write it. So what we are going to do, so the first term by term either solve, or let's open this up. Okay, del 2 theta over del x square phi n x, this is the function of x, dx. Okay, plus integral of, now since d2 theta, first write it very clearly, d2 del 2 theta over del y square phi n x dx, all right, 0 to 1 is equal to 0, right? So what we are going to do now, this you will integrate by integration by part, integration by parts. So while you integrate by parts, you have to take first and second. So this first, and let's say second is this. So this is second function and this is first function. Okay, second function we have taken because del 2 theta over del x square you can integrate, and if you will integrate you will get del theta over del x. Now after writing this, what you with the way 0 to 1, alright, 0 to 1 we have to integrate. So let's take, so first function means phi n, and integration of second, that is del theta over del x. So evaluated at x is equal to 0, lower limit x is equal to 1, minus, so integration by parts we are doing, minus derivative of first. So derivative of first is d phi n, this derivative of first, okay, d phi n over dx, and integration of second means del theta over del x. All right, this integration over x 0 to 1. So this is the first, this we have done. Now this second one that we are going to do here you see, since phi n x is only function of x, with respect to his we are integrating this del 2 theta over del y square. So y is independent of x, both are independent variable, so we can take del y square outside. Okay, del y square outside. So what we will do, del y square outside, so d2 over dy square. Now integral of 0 to 1, and this theta and this phi n x. Okay, so this is the function of x and theta is function of xy both, so we will keep it here, and d2 over dy square is independent of x, this operator, so we have taken it out. So phi theta phi n dx, okay, is equal to 0. Okay, now let us proceed further. So we will write it as here. Okay, all right, so let's move ahead and get the values. So this del theta over del x phi n we have to evaluate, obviously. Just we have commutative, product is commutative, so phi n, it's common, this common thing that you will write the phi n later on, and this one is earlier. Okay, early, so you have to write this before and this right you have after. So this is x is equal to 0, x is equal to 1. All right, because this is kind of unknown and phi n is known, so known after and unknown first. Minus this you will integrate again by parts. This is second time you will be integrating again by parts. So what you will get, this theta, this, suppose again we have taken this as second, and this phi n first. Okay, so this is first and this is second. Okay, so this so first second we have to do now. So all right, so this del theta over del x, so first you will write d phi n over dx, and integration of first second, that is del theta over del x. If you integrate it, then you will get theta only, because this is the derivative of theta. So this will go this will be evaluated x is equal to 0, x is equal to 1 minus derivative of first 0 to 1, derivative of first means d theta, derivative of first, that first we have taken all right, so the first we have taken this, so derivative of first, that is d2 phi n over dx square, and integration of second, that is theta, you have to integrate it with respect to x. So this is, and this plus this, you see, then I have this one is this integral. See, this is the finite Fourier transform of variable, that this we have discussed, finite Fourier transform of theta, and this could be transformed into theta n by taking, just we have explained right here, this theta xy transform to theta ny. How we have shown it right here. Okay, see here. So this theta phi n means integral theta phi n is equal to theta n y. So we can write it easily. So this is theta n y. Alright. So this is theta n. So d2, so plus d2 theta n over dy square is equal to 0. So this is what we got. Okay. Now if you see this one, as we know, the phi n at 0 as well as phi n, this basis function, at 1, both are 0, because this is phi n. What is phi n? Phi n is equal to root 2 sine n pi x. So at x is equal to 0, this is root 2 sine n pi, sine 0, this will be 0, and at 1, this is root 2 sine n pi, that is also 0, so this is 0. So if you put x is equal to 1, then this is 0. If you put x is equal to 0, then this is 0. So this term will go away, 0. Okay, this term will go away, 0 means this will vanish. Okay, now the second boundary term, this one, boundary values are coming as 0, x 0 and x is equal to 0, x is equal to 1, so these are called the boundary terms. This is also going to be 0, and let me tell you why. Because if you see, this theta is equal to 0, x is equal to 1, d phi n d over dx we don't know, but this theta, this could be finite, d phi n over dx, because this will be the function of cos, but this theta is equal to 0 at x is equal to 1. See the problem. See the problem. This theta is equal to 0 at x is equal to 1, and theta is equal to 0 at x is equal to 0, right? So due to theta, this term also go away. So theta is equal to 0. Now this due to theta, this time due to theta. Earlier this due to phi n. So this, now theta is equal to 0. Since theta is equal to 0 at x is equal to 0, so this second term, since theta is equal to 0 at x is equal to 1, and theta is equal to 0 at x is equal to 0, so this term also will reduce to 0 minus 0, that is 0. So only we are left with the final term. Okay, this one and this one, right? So writing this, so this implies this equation further, theta d2 phi n dx square integral 0 to 1 dx plus d2 theta n dy square is equal to 0. So this is what we are getting. All right. Now we need to understand this. Okay. Phi n, we know what is phi n. So phi n, now we have to evaluate this del d2 phi n we know. So we can evaluate this d2 phi n over dx square. So let's put the value of here phi n 0 to 1 theta. So d2 phi n value is root 2 sine n pi x dx square dx plus d2 theta n dy square is equal to 0. Now this will give us 0 to 1 theta. Now we have to differentiate twice. So if we differentiate it first time, we will get n pi cos n pi x. Second time we will differentiate, then we will get cos of minus sign. So minus sign, okay. So let me write it. So root 2 we can take outside, and sin n pi x first time differentiates, then n pi will come. Second time differentiate, then again n pi will come, and minus sign of course will come. So minus sign I am putting here, and n pi is square. And first time if you differentiate, sin become cos, and then second time if you differentiate, then cos become sin. So sin n pi x. Alright, so this would be the second 2 times derivative of this dx plus d2 theta n dy square is equal to 0. Okay, sure. So this is 0 to 1, further simplifying 0 to 1, okay, and minus root 2 theta, alright, and n pi is square, and this is sin n pi x dx plus d2 theta n dy square is equal to 0. Now as you understand that this 0 to 1 root 2 sin n pi x is nothing but phi n. So it returns the value, means a phi n function, because sine derivative of sine is cosine, then cosine derivative of cosine is again sine, it will return the value of phi n. So what would be theta written, and this phi n, okay, this and this become phi n, okay. So minus n pi whole square, this is constant, so we can take out, let me raise this is constant, so we can take out n minus root 2 we have included in the definition of basis function itself. So this is n pi square, alright, n pi square, and this theta and phi n dx plus d2 phi n dy square is equal to 0. Now this is the inner product of theta with phi n with weighting function, weighing function 1. So this with the, this is the inner product, and this has transformed, this will transform theta to theta n. As I told you, the inner product, this theta and phi n will be converted into this theta phi n integral 0 to n, this will be converted into theta n. So this integral 0 to 1 theta phi n is nothing but theta n. So this is theta n, n pi whole square. So see, minus sign is also there, so minus n pi square theta n plus d2, and here this is also theta n, right, because this theta n, alright, so this is also theta n here in this term, this is also theta n, so theta n, now this is theta n, so this is d2 theta n over dy square is equal to 0. What is it? This is ordinary differential equation. How that has come? By taking finite Fourier transform of PDEs, okay. So what is, and this could be easily solved. So this is the means ordinary differential equation d2 theta n dy square plus minus n pi square theta n is equal to 0. Now we need to solve this one. Okay, and once we solve this one, we will get this theta n is the function of what there, theta n function of y, and this is nothing but c n y. Okay. So we will be able to get the value of this theta n. Now this is the differential equation that we have to solve. Okay, so this is the differential equation. So see the beauty of finite Fourier transform, it has converted the partial differential equation to ordinary differential equation. All right, so this is the thing that we must understand. So I will stop here, and this is in this lecture I told you how to take the finite Fourier transform of variable and how to take the finite Fourier transform of, once we take the finite Fourier transform of variable, it will be the reducing the function to one less independent variable, and correspondingly we will take the Fourier finite transform of the PDEs, and that will convert it into ordinary differential equation that could be solved further. So after this, how to proceed is very easy. So the foundation has been set for this, and how to calculate the eigenfunction or basis function, we will take this into the next class. Thank you so much. Please subscribe my channel if you like, and share amongst your friends.